Classes in Statistical Mechanics. Lectures by Professor George Phillies, based on his book, Elementary Lectures in Statistical Mechanics, Springer Verlag, 2000. And today, this lecture is Lecture 19. I'm Professor Phillies, and we are continuing today with our discussion of liquids. And we will actually begin back in chapter 19. And in 19 we discussed distribution functions, and we got as far as last time as equation 19.15, page 270, which explains what the potential of average force is. The first thing we're going to do is an example of how you would use a distribution function. We've sort of skipped around the technical question of where you get them from, is to look at a simple application where we use a distribution function to calculate the average energy of a molecule in a liquid. The energy of a molecule in a liquid is given by equation 19.16. And 19.16 has two parts. There's a kinetic energy part, which is exactly the same as the kinetic energy of the molecules in a gas. And then there's a potential energy part, and I've written the potential energy part as a sum of terms U sub ij. I and j each go separately from 1 to n. And I've chosen the normalization of uij, so you put a half in front, so when you add U12 and U21, you get the total potential energy of the interacting pair. So what is the average energy? Well, we're going to write an average. That's done in equation 19.17. So we do a sum over all of the allowed states. And the sum over all of the allowed states in 19.17 is the integral over all of the positions and momenta of all of the atoms. It's integral drn dpn. Then there's a 1 over n factorial, which is the fact the particles are taken to be indistinguishable. There's a 1 over h to the 3n, which is the Kirkwood-Wigner term, which comes in from quantum mechanics. And then there's the object in big parentheses, and the object in big parentheses is what we're averaging. And so we're averaging a sum of the kinetic energy plus a sum of all the potential energies. The next line is the normalized statistical weight for the calculation. On the next line in the denominator, you see capital Z, the configuration integral. You see a factor of 1 over n factorial. The particles are still indistinguishable. And you see a factor of 1 over lambda to the 3n. And that's the factors of h and the integral over all of the momenta of all of the particles. So the denominator of the bottom of the second line of 1917 is just the partition function. In 1917, the numerator is a sum of the kinetic energy terms and the potential energy terms exponentiated. That's the statistical weight of a given state. So how do we do this? Well, if you look up at the first line of 1917, it's a sum of terms. And so we use the rule from back about the second lecture that the average of a sum is the sum of the averages. And so we can take the numerator of 1917 and split it into parts. And one of the parts, which is what we get in 1918, is the average over all of the kinetic energy terms. And so in 1918, the top line is what the average over all of the kinetic energy term actually looks like when we write it out. I have done one thing to emphasize, that is, if you look at the integrals in either the numerator or the denominator on that first line, they're integral dpn, and everything that depends on momentum. And then there's an integral over the positions and everything that depends on the positions. And I did the same split in the denominator. You notice the integrals over position are the same above and below and cancel. And the integrals over momentum are the same integrals we did for the capital N power N atom ideal gas. And therefore the kinetic energy contribution to the average energy is just the same as it was for the ideal gas. It's 3/2 nkt. That cancellation of positions is very general, and it would occur, for example, if we put in some other function instead of the kinetic energy, some other function of momentum. One of those functions could be a delta function in p minus p0, in which case we'd be calculating the statistical weight of getting each value of p. And that statistical weight is independent of the potential energy. That is, the distribution of momenta in a fluid, a condensed fluid like water, is the same as it is in an ideal gas. That's actually been confirmed experimentally using neutron scattering. If you look at the instantaneous momenta of the molecules in a liquid, as opposed to how long it takes them to travel some moderate distance, you discover it looks just like an ideal gas. Okay, so there's equation 19.18, and 19.18 gives us the kinetic energy contribution to the average energy. Now, the other alternative is to say we will calculate the average value of the potential energy terms. Yes? Now, to do that, we take advantage of a feature. And the feature is that all of the potential energy terms are exactly the same. So there are, if you look at Uij, there are n times n minus 1 different potential energy terms. But they're all the same as each other. And therefore, if we evaluate any one of them, we can just multiply by how many of them there were. That is n times n minus 1. And that is the lead n squared minus n in equation 19.19. Then, and so we're taking the average of one of those terms, say U12. The factor of 1/2 at the front of 19.19 arises because U12 and U21 are both contributing to the energy of the system as a half. And I suppose there are several ways of doing this depending on exactly how you normalize the energy. Notice that in 19.18, I'm going to step back a step, the last term on the top line is a minus beta, and there we've taken I less than j, and so there's no half. In 1919, I think there's a typo in the exponential of the statistical weight. There should, if it's just summation I not equal to j, there should be a half there, I believe, shouldn't there? You should check that. Okay, so we have now reduced this to 19.19. Getting to 1919, the momentum integrals that were in 19.17 all canceled against each other because they're the same in the numerator and the denominator. The n factor 1 over n factorials are the same in the numerator and denominator and canceled. And what we're left with is the configuration integral in the denominator and an integral over all of the positions of all of the particles, potential energy of one of them times the position part of the statistical weight. We now take a step forward and do a simplification. And the simplification is to say that if you have that integral over all of the particle positions of what you have there, that can be rewritten. Namely, there is an integral dr1, but everything can be written relative to dr1. There's nothing in the integral that's just a function of where particle 1 is. So that integral just gives you a factor of v, the volume. Then there's an integral dr1, 2, the distance between particles 1, 2, and that acts on the u12, that is the potential energy. All of the other integrals, positions of particles 3, 4, 5 out to capital N, can be taken to the other side of the u12 because u12 is a constant with respect to them. And if you do that, you end up with an equation which is in fact identical to 19.7. Or if you prefer, it's identical to 19.3. That is, in 19.3, there's an integral over all of the positions of the all of the particles except the first little n. Here little n is 2. And times e to the minus beta u divided by z, and that gives us a specific n-particle distribution function. You can rewrite the specific n-particle distribution function with some work in terms of little concentration to the n times the n-particle radial distribution function, that's seen in 19.5. And when you do those replacements, you get equation 19.19. That is, there is a two-particle distribution function. We're averaging the potential energy over the two-particle distribution function, and the n times n minus 1 gives me a factor of n and a concentration. The average energy of the system, combining equations 19.18 and 19.19, is then seen in 19.20. In 19.20, r is the variable showing the distance between the two particles in the two-particle radial distribution function. There is the average energy, and we have now used the average energy. We've now rather used a distribution function to get the average energy. So there you see a distribution function in use. What does the distribution function do? It tells you the probability of finding two particles a certain distance apart in a certain vector direction. In many cases, for simple liquids, the radial distribution function is only a function of the distance between the particles. If the particles are spheres, that's true. If the particles have shape, the distribution function will depend on the orientation. Here are two particles. The distribution function will depend on the orientation of the two particles and their angular position with respect to whatever direction you're using to write the orientation vectors. Okay, we are now going to chug ahead and do something else. We are now going to calculate the pressure one more time in a different way. And the reason we are going to calculate the pressure one more time in a different way is that it shows us a trick where we get our answer indirectly by rescaling some variables. So what we do to start this is start on an equation 19.21, which says the pressure is the thermodynamic derivative of the Helmholtz free energy with respect to volume. But the Helmholtz free energy in the canonical ensemble is e to the minus beta, e to the minus 1 over beta log Q. And therefore, we end up with the second term in 19.21. Okay, well, we have a derivative of log Q with respect to the volume. And what I do is to say, I'm actually going to take the derivative of log Q. Instead of evaluating Q and then taking its derivative, I'm going to take the derivative of Q before I evaluate it, and therefore I get 19.22. Well, what is the derivative of the log of a function? It's the function itself in the denominator, and that's what you see at the bottom of 19.22. And then there is ddv. The ddv is buried inside the equation a bit, ddv of the function. So there is the pressure written in terms of the partition function and a derivative. Of course, that's very nice, but you then sort of say, how are we going to take the derivative? The first issue is the variable you're taking the derivative with respect to is found only in the bounds, not inside the function. And that's not impossible to evaluate. In fact, if you know how to take the derivative, a parametric derivative of a function, you end up with, if the function's an integral, you end up with the integral of the derivative and the function evaluated at the two endpoints. And you may or may not know Feynman's comment. He learned this in his high school calc class, and he carefully memorized the formula. And when he was doing his doctoral thesis, he realized he knew the formula, and this is how he won his Nobel Prize, something he learned in high school. The question is, how do we actually do this derivative? Well, one approach you can do is to say, since the derivative only acts on the endpoints of the integral, we only need to evaluate the function at the endpoints. That's a little tricky. The other thing you can say is, well, you know, the pressure depends on the volume, but it really doesn't depend in any detail on the shape of the container unless you're really unreasonable about the shape. I mean, if you say the volume is the volume of this room, but it's been stretched out to a soda straw that is 2/3 of an atomic diameter wide, and that makes it really, really long. And therefore the atoms are being crunched by the two walls because it's like vices holding them in place. Well, then you'd run into some issues with the pressure. But as long as the volume of the room is some reasonable shape, it doesn't matter very much what the shape is, and therefore we shouldn't have to worry about it. So what do we do to make the volume not appear in the limits of the integral? And the answer is we do a change of variables. And the change of variables is shown just above 19.23. We take each coordinate of each atom, x, y, z, etc., and we replace x with a new coordinate, x prime, and x prime is x over v to the 1/3. Okay, so and then dx is dx prime v to the 1/3. So that's how I replace each of the differentials with the new differential. And I also realize that if I've changed the coordinates, I have to change the bounds. And the bounds are now, for each volume integral, the new coordinates are the old coordinates as a volume element divided by v. So the new bounds are 0 to 1. Yes? Mm-hmm. And the new coordinates are inside. And there's an e to the minus beta u, which is written in terms of the new coordinates. And there's a z. And I have a d dv. So far, so good? Well, g, how are we going to take the derivative with respect to v? And what we realize is there are two parts, and one is the d dv can act on that v to the n in the front. The v to the n appeared because I changed the differential elements in all the integrals. And the other is that the d dv can act on the e to the minus beta u. Mm-hmm. And so we actually, in 1925, take those derivatives. And when we take the derivatives and rearrange a bit, we notice that the numerator of 19.23, the thing in square brackets, is just capital Z times v to the n, and d dv v to the n is n v to the n minus 1, which I wrote slightly oddly, deliberately. And the other thing that can happen is the ddv goes inside the integral in 19.23 and attacks the exponential minus beta u. And when it does that, it brings down a minus beta du dv. And then the e to the minus beta u sits there. Okay, go down to 19.25, the second line, it's a fraction, the numerator. There is a du, d variable dv. That's a du dv. That's what happens when we took the derivative with respect to volume of the statistical weight in 19.23. And I have used the chain rule to split out an r prime I v to the 1/3 summed over I. That's the chain rule. And so du dv becomes du d variable dv. Well, can we do those derivatives? Yeah, the derivatives gives me a du dr and an r over v and a 1/3 if you actually crank through those. Yes? And so with this transformation in 19.26, which is just a freshman calculus transformation, you get to equation 19.27, which is the pressure of the liquid has two parts. It has an ideal gas part, KTN over V. It has this other term, which has a beta over 2 and a 1 over 3V, and it has a du dr times r summed over all of the pairs. Yes?
Mm-hmm.
Okay, well, all of those terms, du dr times r, are the same, because each potential energy is only the function of 1r, ij. It's the same function each time, and therefore you can replace the sum on I and j with n times n minus 1 of its copies. Do you notice there's a certain theme here? We'd take advantage of the fact that all the particles are the same. And that gives us a factor of n times n minus 1. And then, having said that, we stick in the derivatives. Yes? And the last thing we do is to say, well, we're doing an integral over all of the particle positions of this du dr times r, but we've replaced all of the r's with r12. So r12 is a privileged variable because it's used to integrate not only over the statistical weight, but over this other function. All of the other variables, r13, r14, and so on, are only integrating over the statistical weight, the e to the minus beta u, because that's the only thing that's a function of r13. So we take the constants with respect to r13, r14, etc., out in front. The constant is the integral dr12 times various things. And then we're left with integral dr13, dr14, etc., and it's integrating e to the minus beta u over z. That's in 19.27. That is, all of the variables other than r12 are just integrating over the statistical weight. And we have seen that before, now several times, and we see it, and it's basically the statement that from equations 19.3 to 19.5, we have an integral over the positions of all of the particles of e to the minus beta u, and that's simply the radial distribution function. Yes?
Mm-hmm.
And so we can replace all of the integrals other than dr12 with the radial distribution function. We can do the integrals as is shown in 19.28. And when we plug 19.28 into 1927, we get equation 19.29, in which there is a typographic error. The typographic error in 19.29 is that the variable of integration is over the scalar distance r12, not over the volume integral. The fact that it's over the scalar distance corresponds to the fact, gee, this function is independent of direction r12 hat, so I can just do the angular integrals d theta, d phi, and I get a factor of 4 pi. The 4 pi is out in front. Part of the 4 pi has canceled a 1/2. Then, since I'm now in scalar coordinates rather than dr12, the integral dr12 is actually r squared dr, and I pick up an extra factor of r squared. So if you look at 19.29, there is an r12 cube. The cube appears, there's one factor out of, this is the derivative that gives us the pressure, and there are two factors of that out of the this is an integral, and a spherical integral, and we've written it out in terms of the scalar coordinates, and therefore it's r squared dr, and it's all there. That's 19.29. Okay. What can we say about this calculation? Well, there's no reference at all to the atom wall potential, and therefore we've implicitly assumed that the atom wall potential can be ignored, except it tells you how far the atoms can move. The reason we know this is true is the integral we did way back about chapter 6, where we put in the notion that, gee, there's an atom wall potential, it's strong and attractive, and the gas condenses on the wall and the pressure crashes. You can test that experimentally. It works. That's how gas masks work. They have this huge filter area of activated charcoal which absorbs all sorts of things, and all sorts of things are absorbed by the activated charcoal, and therefore when they come through to the far side, the stuff you're breathing gets through to the far side, the partial pressure of various noxious things has been dropped to near zero. It really works. I've used one, gas mask. Okay, however, having said this, we now have this radial distribution function, and it is we have not yet said anything about how you would conceivably calculate it. You can try to set up cluster series for radial distribution functions, and there are various ways of doing this. The problem with doing this is that you can set up cluster series, or you can set up an integral equation which gives you completely accurately G12, the pair distribution function. The problem is that the integral is an integral over the three-body distribution function, and if you keep looking at this, you discover there's an infinite regress in the process. Now, there's several ways to solve this, one of which is the Kirkwood superposition approximation, which we'll get to in a bit. You might say, well, can't we measure it? And the answer is there are experimental techniques for measuring the pair distribution function. There are not, the last I looked, there are some marginal tricks with X-rays and NMR that give you pieces of the three-body distribution function. That's true since I wrote the book. So the book is a little out of date on that discussion. However, it turns out that if you want to calculate all sorts of things using the distribution function, you can actually calculate, you really only need most of the time the pair function. Okay? Furthermore, if you ask what does G2 of R look like, it's dominated by the fact that real atoms have hard cores. There are corrections because there's potential energy other than just the hard core, but they really, in some sense, are corrections. In fact, there are some people will just approximate G of R as its hard core form, which you can get out of Monte Carlo or molecular dynamics. And you can then ask, I guess we should say, what does the radial distribution function look like? The answer is it has wiggles. At very short distances, well, two atoms can't overlap, and so G of R, the probability of finding two atoms a distance r apart, is 0 if the two atoms are significantly less than their own diameter together. Something like this, the probability is 0. However, once the two atoms are their own diameter, 2 radii apart, that's allowable. And now the atoms pack. And what happens, in fact, is here we have an atom, and approximately speaking around it, there is a at high liquid densities, there is a close packed shell of neighbors, which will contain most of the time 12 neighbors. That the positions fluctuate. And that gives us, it's actually an icosahedral shell because there are 12 of them. It's not a spherical shell. And then there will be a second layer packed on top of the first, and a third layer packed on top of the second. However, because these things are fluctuations, it's not a solid spherical shell. As you go further and further out, the spherical layers are smeared out more and more, and they tend towards the behavior of G of R at very large distances. At very large distances apart, G of R is just 1. Now you might ask, gee, how large does G of R, does very large have to be? And you can look in a lot of the competing books which will tell you that, after about 4 or 5 shells, there's nothing left. That's really incorrect. Paul Whitford, who was at that time an undergraduate, and I, did molecular dynamic simulations of a 2-component Lennard-Jones fluid. This is not hard sphere, but it's actually fairly close. And we started out, and the first question is, well, if you see any structure in the liquid, is it maybe something that was left over from the start of the calculation? So the first thing we did is to take the fluid, this is computationally, up to about 50,000 in natural units. Natural units, let's convert that. 50,000 is we first took the fluid up to about 5 million Kelvin. And we then allowed the atoms to move until they'd crossed the container several times. And because the atom, and at 5 million Kelvin, you have assuredly destroyed any structure. The freezing point of the solid is about 1 in natural units. So it's about 5 million Kelvin you cannot do experimentally because the Lennard-Jones atoms are so impolite as to notice they're in a plasma and ionize. Well, our atoms didn't ionize. And we then cooled things down very slowly, and we eventually cooled it down through the freezing temperature, but since we've cooled it the right way, we ended up with glass or something close to a glass. And one of the things we measured was the radial distribution function. And so you see 0, and you see the first maximum and minimum and maximum and minimum. And I realized, gee, how do we plot this so we can see the structure? And one answer would be you center the plot at 0, at 1, and you blow up the linear scale. And my answer was, we'll plot G of R minus 1. After all, we know it goes to 1 at large distances, so we can subtract that out. And now we'll take the magnitude of that, because G of R minus 1 is negative in places. There are places where the density is lower than average as well as higher. And we'll put this on a semi-log plot so that small features get blown up. And what we realized was that we could easily see the 4th, 5th, 6th, 7th, 8th. And so we redid the calculations with a sufficiently large sample, so the box was large enough that the walls of the box, we actually used what are called periodic boundary conditions, does not get in the way. And because of the periodic boundary conditions, we were able to see well over a dozen coordination shells. The height of the shells falls exponentially with distance out, except for the first few shells, which have a complicated structure. We were also able to demonstrate that if you cool this thing off, eventually you start getting interesting structure in G of R. The interesting structure, that is something that is not like the liquid, appears at about T equal 2, twice the melting temperature. It's reproducibly stable. After all, we formed this stuff by coming down from 5 megakelvin. It grows as you make the system colder, and the interesting structure appears to have septahedral order, 7-fold order. There are essentially no known examples in nature or theory of septahedral ordering, so there's not much to be said about it. And we didn't pick out in more detail what it was other than septahedra. Okay, so there is G of R and it has structure, and if in a liquid the structure is actually quite long range. Well, it's not 1 over R long range, but it's 10 or 15 atomic diameter range, not 4 atomic diameter range. Okay, let us chug ahead to chapter 20. And we have now reached chapter 20, and we are at least going to discuss charging processes. When I say charging process, I do not mean electrical charge, though you can use this approach to treat electrostatic systems. The notion is we will identify one atom in the box. And the one atom in the box has a different potential energy than all of the others. The different potential energy is the same potential energy as all of the others, multiplied by a parameter lambda, and lambda goes from 0 to 1. Now, what does this mean at the two extremes? Well, if lambda is 1, the potential energy of all of the atoms is exactly the same, and we have n minus 1 atoms originally, plus 1 different atom that is now exactly the same as the rest, and it's an n-atom system. If we drop the potential of lambda down to 0, the potential energy of that atom with respect to all its neighbors goes to 0. And we now have a ghost atom. It doesn't interact with anything, it just bounces around in the box. So it's a ghost. And in between, we have something that interacts more or less strongly with its neighbors. Charging processes, that is, the use in modern statistical mechanics, is properly ascribed to John Gamble Kirkwood, who was the leading statistical mechanician in the United States in up through almost 1960. Much of what you read about liquids is due to Kirkwood. The stuff we're doing in particular. Charging processes, however, were actually introduced by Josiah Willard Gibbs. They're found in his book. He had a completely different use for charging processes. His issue was, how do we treat within the domain of statistical mechanics an irreversible process? And the first point he makes is that, well, the equations of motion are time reversible, and therefore if I just do a calculation on a canonical ensemble system, the equations of motion are time reversible, and therefore there is no possibility of discussing thermodynamic irreversibility by looking at a single system. Yes? So what will we do? Well, in order to have irreversibility, you need two systems at two different temperatures. And having said we have two systems at two different temperatures, we then bring them ever so delicately into contact with each other. And his approach to bringing them into contact with each other was to say we have a potential energy of interaction which we can turn on and off by making it weaker and stronger. And when we do so, we can ask, on the average, start off, there are two ensembles. Could be imagined as, for example, two types of gas in the same room, and the gas of species A and of species B is non-interacting. So the two gases can actually be at two separate temperatures because they can't see each other. And now we turn on the potential energy of interaction, and there will be interactions and there will be work done, and we ask what is the direction of the energy flow. And what he says, and it's an approximate argument, he's very careful on that, is that most of the time the energy will flow from the hotter system to the colder system. And he discusses this as a flow of heat and shows that you get all of the expected behaviors if you do this. Go first, I'm good? Well, that is Gibbs using a charging process to treat thermodynamic irreversibility, and incidentally telling you, if you want to do statistical mechanics of irreversible processes, what the calculation, approximately speaking, should look like. Okay, we are now going to use the charging process to calculate the chemical potential. We are now going to use a charging process to calculate the chemical potential of the system. And the chemical potential we are going to calculate is some sort of a fluid, and we're not actually being very precise as to what the fluid is. So the chemical potential in the canonical ensemble is partial of A with respect to N. And A, of course, is minus kT log Q. So that's equations 20.4 and 20.5. However, there's one minor issue where we actually have to be a little careful here. Q, the partition function, is only defined for integer numbers of atoms. So we have written partial of Q with respect to N as a derivative, but you should realize you can only either do have an atom or you don't. And therefore, you actually have to write the derivative as a difference equation, and that's done in equation 20.6, where mu, the chemical potential, becomes log Q, evaluated for N, minus log Q for N minus 1, that's delta Q, divided by delta N, but delta N is 1, so it's not written down. Okay, so there's Q, and we've written it as log for one Q versus minus log for the other Q. However, the partition functions, if you think about those for a moment, the partition functions, when we average, really, they're the momentum things that cancel, and what is going to be left is what is seen in equation 20.7. What is left that matters are the two configuration integrals for n particles and n minus 1 particle. And so mu is the ratio, is based up to some normalizations, is the ratio of z for two different values of n. Before we go further, I think I'd better say a little bit about the first few equations in the chapter. Equation 20.1 is actually the potential energy with atom 1 singled out as the atom that has the charging potential. Equation 20.2 is an n-particle specific distribution function. It's the relative likelihood of finding various particles in different places correctly normalized, except we've put in the fact that one of the potential energies contains the charging potential. And I also remind you of the relationship between the distribution function and the radial distribution function. That's equation 20.3.
Question.
Yes?
For 20.1, do we want to specify that I not equals J?
In the potential energy, the first term, yes, it actually is I not equal to J, though you could always say UII is a 0 and not worry about it.
Okay.
There are some interesting things if you don't do that, and if I recall correctly, in quantum, if you don't specify that electrons don't interact with themselves, you get some peculiar divergences, which you have to be careful about. Feynman explained how to do that, too. Okay. Well, having said that, we then ask, what does the configuration integral look like for different values of lambda? And so equations 20.8 and 20.9 are the configuration integral with lambda equal 1 and with lambda equal 0. And you notice in the central integrals, the integrals in the center of those two equations, you either just see summation u1j, which is atom 1 interacting normally with all of its neighbors, or you don't see that term, and that's the ghost atom 1. And those are the configuration integrals z for n and n minus 1 atoms. Now we do a math trick. And the math trick is to say that integral df dx over f of x dx is the logarithm of the function evaluated at the boundaries. Yes? So the logarithm of the function, this ratio of function evaluated at 2 points, can be written as a specific integral seen on the left side of equation 20.10. Where is that thing useful? Well, refer back to equation 20.7. In equation 20.7, you have a function which is evaluated, logarithm of that fraction, and in the numerator of the fraction, the function is evaluated at capital N, and in the denominator, it's evaluated at capital N minus 1. So here we have a logarithm of a function, rather, evaluated at 2 points. That's the same as the right side of equation 20.10, and therefore we can replace it with what you see on the left side of equation 20.10. That's shown in equation 20.11. And the chemical potential becomes a ratio, becomes a sum of two terms, and there's a logarithm of v over n lambda cubed, and that's the ideal gas part. And then there's an integral from 0 to 1 d lambda of z. Yes? So we have dz d lambda over z. That's the derivative. That's the logarithmic derivative. We're going to focus on that second integral. And that second integral, to make clear, is the thing shown in 20.12. Because 20.12 is the non-ideal part of the chemical potential. It's the part of the chemical potential that arises from interparticle interactions. Okay, so we're actually going to evaluate that. And in order to evaluate it, the first thing we do is to say, we can write out the derivative, and d lambda, and that's what is done in 20.13. And in 20.13, the d lambda of z has brought down the potential energy from e to the minus beta u, and there's a statistical weight, which is a function of lambda, and then down in the denominator, there is a statistical weight, which is the configuration integral, the normalizing factor. Okay, when we took d lambda in 20.12 of the configuration integral, that only acts on the statistical weight. And what it does is to bring down part of the potential energy as seen in 20.1. It brings down the sum e to the u1j. And that's the sum in the front of 20.13. However, if you think about this for a moment, you realize that all of those u1j terms are identical except for label. And so I may replace the sum on the u1j's with n minus 1 copies of u12. Furthermore, in doing this integral, you notice that that u12 is only a function of r12. It's not a function of any of the other variables, and therefore in evaluating u12, what I can do is to take the dr12 u12 outside, and all of the other integrals view that as a constant and go inside, and you get equation 20.14. And in 20.14, you see there's an integral 0 to 1 d lambda from the start. There's an integral dr12 u12. That's something that actually depends on r12. And then, next line, open square brackets. There's all this stuff, and only the things on these lines depend on integrals dr3 to drn. The things on the top line are independent of, for example, r13, and therefore the things on the top line are constants with respect to that integral and can be taken outside. And having done this, we can rearrange, because the bottom integral is in fact the two-particle radial distribution function. It's this very complicated pattern of symbols, but it is the radial distribution function, and with that replacement we get 20.15 for the excess chemical potential. There's only one problem with equation 20.15. It asks that we supply the pair distribution function for an arbitrary value of lambda. Not for lambda equals 0 or lambda equal 1, where we can measure it, but for an arbitrary value of lambda. And you can't measure that because we can't manufacture ghost atoms in the laboratory, especially not tunable ghost atoms. So we sort of have to ask, well, what should we do? And in a certain sense, the answer to what should we do is we have to do something clever, and that is discussed in the next section, which we will take up next time.